Welcome to ME 357, System Dynamics. I'm the instructor for this course, Dr. Mahoney, and there are two textbooks that I recommend as part of this course. The first one I'll say is more of the required textbook, the ODEs System Dynamics book. There is the fourth edition is the most current one, but I would say for this course that the second or the third would also be perfectly acceptable to use. You'll notice that the newest printing is all the way from 2004, so it is a bit dated in some of the technology that it employs. So I also recommend the Palm System Dynamics book as another reference for the course. The ODEs book I'm going to use a lot more to have examples from and lean on for some of the things in the text. And the Palm book is going to be a little bit more updated in using MATLAB and other technologies to solve our system dynamics problems. So in this section, I'll be talking about what is and what is the purpose of system dynamics, what the course is all about, and a little bit of understanding how system dynamics is applied to real-world problems in mechanical engineering and outside of mechanical engineering. So, system dynamics. What we're going to be doing in very general terms in a system dynamics course is we are trying to describe real-world dynamic systems in terms of these connected, idealized components with simple physics relations. Or it could be other types of relations. Mostly what we're going to be looking at are mechanical systems that are going to be put together with springs and masses and dampers. And we're going to see how these elements interact with each other. However, we'll also be spending a good amount of time on electrical systems, where we're going to have resistors, capacitors, inductors as our basic elements that are going to be put together. And we're going to be making schematics and seeing how these components interact and turning our real-world system or our schematic into mathematics that describes the situation that we have. The math is going to come in the form of differential equations, and more specifically, ordinary differential equations for this course. Everything will be dependent only on time. There will be only one independent variable. Now, we will get into, in follow-up courses to this, like vibrations, systems where we will get a partial differential equation. We're going to have our dependent variables dependent on time and spatial variables as well. But we're going to stick to entirely ordinary differential equations in this course. So we use our schematic, our real-world system, and we translate it into an ordinary differential equation or a system of ordinary differential equations that are going to describe how the system is going to behave in time. Everything we're talking about here is going to change over time, and that's the dynamics part of the systems that we are analyzing. And really, what's the point of what we're trying to do? Well, we're trying to, in essence, predict the future. We want to know what is the position or the voltage or the pH or some other variable that changes in time in our system once we start our timer, once we start at time equals 0 and we go forward into the future. We want to know what is the system going to be doing. And this is going to have a lot of utility because we might want to simply be able to predict what it's going to do, or eventually we might want to change what it's going to be doing. We might want to modify different elements in the system in order to elicit a different behavior as time goes forward. And we'll be getting into that as we look at the breakdown of this course. And really, in essence, what a system dynamics course is, and if you take the follow-up, the vibrations course, really these courses are applied differential equations classes. We're going to be spending a good amount of time modeling systems, and I'm defining modeling as taking our real-world system and then writing it in these mathematical terms. But really, once we have the math written down, then the procedure is going to look the same of how we do analysis and how we do control of these systems. So really, it's not going to matter once we've translated into the math if it came from a mechanical system, an electrical system, a biological system, or any other type of system that's evolving over time. So the course is going to be broken down into 3 units that are each going to build on the previous one. So we're going to start by looking at how do we model systems? How do we take our physical system, typically physical system, really we're going to focus on mechanical, electrical, and fluid systems in this course, a little bit of thermal. How do we take these real-world systems and break them down into interacting elements? Again, in like a mechanical system, that would be springs and masses and dampers, and we'll see the other types of elements we have in different systems. How do we break them down into these simple components and then see how these components are all going to interact? And how do we simplify these components, simplify our models, so that we can go from the real world into our equation? So we make some sort of schematic, and then we'll have some process of going from that schematic into creating a system of differential equations. Once we have our system or one differential equation, then the last part of the modeling step is we're going to take that equation and we're going to create what we're going to call either a transfer function out of it, or we might take a state space approach to the model. And once we have either the transfer function or the state space, then we have completely modeled the system and we're ready to take it and use it in another step. And that leads us into what we'll look at then in Unit 2. Once we've done the modeling, once we have this equation, once we have a mathematical description of our system, what do we actually do with it? Well, that's what Unit 2 is going to look at. We're going to be taking our equation and we want to use it to make predictions about what the system is going to do as time goes forward in the system. So we are going to be solving systems of equations or using the transfer function or the state space model to make these predictions. So what would we be interested in? Well, we might want to track in a mechanical system the position or positions of different masses over time. In an electrical system, we would be interested in knowing what the voltage and or current is across different elements as time goes forward. In a thermal system, we might want to know what the temperature is of an element as time goes forward. Well, that's really the solving part from the modeling step, from our ODE, is what is this property doing over time? Now, we're going to see in the analysis, we might not need to know necessarily what is that property doing at all points in time, what's its value from time is 0 to time infinity. Sometimes we're really just interested in some features of that behavior. So for example, we might just want to know, well, what's the maximum value that that property is going to hit? Is it going to be above some threshold or below a threshold that we might have for that system? What's the response time? So once we put an input into our system, how long is it going to take before it returns to its starting position? And again, through prediction, we might look at that value and say, oh, that's going to take too long, or yes, that response time is fast enough for what we want to accomplish. And we're going to see how systems behave when we excite it or when we put in an input at different frequencies. And that's going to be looking at Unit 2. Now, some things in the analysis we might not like how the system is going to behave. Maybe its maximum value is too large. Maybe its response is too slow. So then we're going to look at Unit 3, control. How do we modify the system so that its behavior is going to match some desired behavior we have for the system? So we can do that in 2 ways, which I'll classify as passive control and active control. In passive control, we might look at our system and its behavior and say, okay, well, we need to modify some of the elements in our system so that it has the behavior we want. So maybe we're going to swap out some springs, we're going to make them stiffer or looser, we're going to increase or decrease a mass in the system, maybe we'll have a resistor with a higher or a lower resistance so that we get the behavior we want. And this will be what I call passive control, changing the actual elements in the system to get the behavior that we want. But we're going to see that that's not always the best way to change the behavior in our system. We might not be able to modify the actual components of the system, or maybe we want the system to behave one way during the day and a different way at night. So actually swapping out these physical components wouldn't make a lot of sense if there's multiple ways we want the system to behave depending on what the task is. And that's where active control might make more sense. In active control, we're going to look at how do we prescribe an input into our system that is going to elicit a particular response in the system. And by designing our controller, which is going to determine what that input is into the system, we can get out the behaviors that we want, and we can have multiple types of behaviors depending on what we want to do. So that's the basic structure of this class, of going all the way from our schematic to a fully controlled system, going through the units 1, 2, and 3. So how is system dynamics actually useful? How is this applied differential equations class going to have an impact in the real world? Well, I have here some domains, and I have just very simple examples, or sometimes very trivial examples, of where this is being applied in the field. This is a very short list, and it's not meant to be at all exhaustive. So mechanical, which again is going to be what we'll focus on as we are mechanical engineers here. One thing we can do is we could be designing or selecting the stiffness and the damping of shock absorbers in a car or another vehicle. That's going to ensure a smooth ride. And so, for example, the stiffness and the damping you want if your vehicle is intended to do mostly highway and street driving might be very different than if you're designing a vehicle that's meant to be taken off-road and have much more rugged terrain. So how should we pick the elements of our system for that desired task? We'll also be looking a lot at electrical systems. And one thing we'll be looking at there are filters. How do we take an incoming signal, filter it, and get a different output at the end, a filtered output? So we might be getting in some signals that are very noisy. They have a lot of undesired characteristics. And what we can do is design a circuit that's going to take that noisy input, and it's going to maybe be a low-pass filter or a high-pass filter, and then give us on the other side a much cleaner signal. Outside of the kind of pure engineering world, we can describe biological systems in terms of differential equations as well. Really, any system that is changing over time can most likely be described using a differential equation. So in the biological realm, what we could do is use system dynamics, or the types of topics we're going to be talking about, to do infectious disease modeling. We can model how fast a disease is going to spread through a population, and we might be able to change certain parameters about social distancing or masking or hygiene to see how that's going to affect the spread of a bacteria or spread of a virus. Also, we can go kind of at the more micro level at cellular dynamics, and we can look at drug delivery methods to cells. So we can see kind of how fast is a cell going to uptake a drug, and then different ways we can modify that, or how a cell is going to metabolize the drug, and then have a prediction about the effect of that drug. And then at another level, a more macro level, we can create population models to recommend how many deer licenses to distribute in an area every year in order to try to control the population so that it doesn't get too large and it also doesn't get too small. Or the same idea with how many fishing licenses to offer so that we can maintain a steady or maybe a slightly grow our fish population. In the geoscience realm, we can use system dynamics in part to make climate models, and we're going to be able to use those to help predict the magnitude, the severity, and the impact of global type of climate change and see different mitigation efforts that could be enacted and what effect we predict they're going to have on the global climate. Now, as we get kind of outside this mechanical and electrical realm, the complexity of these models does get much higher, and making these predictions does get much tougher. And actually, I'll talk about this in more detail in the 4th unit, where I talk about nonlinear dynamics a little bit and how this complexity makes it a little bit less certain of the predictions we're making out of these models. And as a last field example, in the financial world, we can make economic models using differential equations, and we can use these models to make predictions of what's going to happen if we, for example, raised or lowered taxes. What is that going to do to the GDP? What is that going to do to our unemployment rate or other outputs that we might want to be measuring and we might want to be trying to improve? Also, other inputs we can have in the system, not only a lever of putting taxes up or down, or what if we implement quantitative easing? We put money into the economic system and we see what effect that's going to have on our outputs. What will an adjustment to the federal funds rate do? If we increase interest rates, if we lower interest rates, what effect is that going to have on that overall economic model? Well, instead of just kind of blindly pulling these levers, having a model that tries to predict and describe the system is going to be helpful so that we can have a little bit more of an informed idea of these types of changes that we make to our economic system.